Okay, today we are going to do a proof technique, a new proof technique for sets. All right, and the proof technique is based on 11.24 and 11.25. So let's take a look at these two definitions. The 11.24 is a definition and 11.25 is a metatheorem. And we all know what a metatheorem is, right? What's a metatheorem?
Theorem about theorems.
It's a theorem about theorems. Okay. So first of all, we have to have these we have to know what these definitions are. 11.24 says, let E sub s be a set expression constructed from set variables, the empty set, the universe, complement, union, and intersection. Okay? So that capital E is an expression, and it's an expression of sets with those operators. Then E sub p is the expression constructed from E sub s by making these replacements. Everywhere there's the empty set, you replace that with false. Everywhere there's the universe, you replace that with true. Everywhere there's union, you replace that with or. Everywhere there's intersection, you replace that with and. And everywhere there's a complement, you replace that with not. Now when you do that, then E sub p becomes a Boolean expression. So notice that the types of E sub s and E sub p are different. E sub s is a set expression and E sub p is a Boolean expression. Okay? I guess S for sedicate, P for predicate logic, predicate calculus. And the construction is reversible. In other words, you can go either way. All right, now, so let's do some examples, okay? And we'll go around the room. Who wants to be first? Mason, you want to be first? Yep. All right. 11.24 examples. Okay, suppose this is our E sub s. So the E sub s is this. S intersection the complement of S. All right, so Mason, what is E sub p? S.
And.
I didn't think your name was... What does it say to replace here? It says replace what? This is intersection, right? It says replace intersection with what? With and. So S what? And. Now this is the complement. It says replace the complement with not. So this is not and this is S. All right, now does everybody see how that worked? Okay. Now here's the thing, you guys. This S is a set. This S is a set. But what is this? This S is a, what kind of expression? Boolean is a Boolean expression. Actually, I should have said this S is a set expression. This S is a Boolean expression. So does everybody understand the difference? Okay. All right. So, Kyle, what about this? E sub s is the expression, the empty set. So what's E sub p?
False.
Yeah, it's false. Is everybody clear on that? Okay. Now, so, and you know, we could go through but I think it's obvious how you do this, right? We could go through more examples, but I don't think we need to. Okay, so now let's take a look at 11.25. 11.25 is a metatheorem. Now check this metatheorem out. This is really quite nice. There's three parts to it. Part A, E sub s equals F sub s. Now what's the type of E sub s?
Set.
It's a set. And what's the type of F sub s? Set. So we have equality between two what? Sets. So this is a set equality. Are you with me? So if we have this set equality, E sub s equals F sub s, that is valid if and only if what?
E
Sub
sub
P.
P equals F sub P.
E sub P equals F sub P. Do you realize how slick that is? If you want to prove a theorem about two sets being equal, is all you have to do is make this little substitution. And if that's a theorem, that's a theorem.
But it has to be an expression only with universe.
Yeah, it can only have these yeah, if it has anything else, then all bets are off. Yeah, right.
Subsets make
What
it
about?
equal.
Well, except for B, look at part B.
Yeah.
So you
Part B says if E sub S, it says E sub S is a subset of F sub S, is valid if and only if E sub P implies F sub P is valid, right?
So we can't use subset.
So you can't, well, if you use part B of the Metatherm,
Right.
you can, then subsets will enter into it there. And then here's another one. E sub S equals the universe is valid if and only if E sub P is valid. So there's three parts to the Metatherm. Okay? So let's do some examples of how to use the Metatherm. Oh, this blue marker leaves a residue. Okay, so let's do 11.25a, 11.25a example. All right, so let me ask you this. S intersect the complement of S equals the empty set. Now, what do you think? If S is some set, now what's the complement of S? It's everything that's what? Not in S. So if you take S and you take the intersection of that with everything that's not in S, what are you going to have?
Everything?
Everything or nothing? Is this intersection or union?
No,
This is intersection.
So you want everything in common. There's nothing in
there's
common.
nothing in common.
There's nothing in common, right?
There is nothing.
So that should be the empty set, right? So does this look reasonable? Well, but by this metatheorem, this is valid. This is valid if and only if what is valid?
S and not S
Y-
is false.
Yeah, S and not S equivales false is valid. Are you with me?
But it is.
Now, is this valid?
Yeah.
Which is?
This happens to be,
It's contradiction.
yeah, this happens to be contradiction. We know this one already. So there, all right, boom, the metatheorem, boom, we got this one. We don't have to go through and, are you with me?
We don't have to prove that V isn't denied.
Yeah, well, I mean, yeah, the way to do this directly, you would say, oh, this is equality between two sets, let V be an arbitrary element, and, V is an element of this,
So we
if and only if V,
never
blah,
have
blah.
to
I mean, you can use the metatheorem, you just boom.
We never have to do the let V be an arbitrary element.
Well, no. You cannot always use the metatheorem. There are you can use the metatheorem for some problems, but not.
But we need to use the
Yes, there will be many.
first one.
There will be many. Okay. So how about here's an example of let's do 11.25b example. Okay. Now what about this? S intersection T is a subset of S. Now, what is S intersection T? That's all the elements that are in what? In both in S and in T, right? Now, is that a subset of S? I mean, that makes sense with sets, right?
Yeah.
Because, if you have S and T and they overlap, then it's the ones that are in that overlap region. Well, that is a subset of S, right?
Which is
Okay, but this, what we're claiming is that this is valid if and only if what is valid? Haha. S and T implies S is valid. But yeah, but this is strengthening. We know this already, so boom, now that proves this with the Metatherm. Are you with me? Is that slick or is that slick?
That's like,
All right.
Kind of.
Okay, now you asked about this whole big group of theorems just before class,
I
Josh?
did.
11.20. Look, what is this? 11.26. What? 11.26. Look at 11.26. What is? It's of the form what? One set equals another set, right?
tree of order.
But if you convert this to E
That's
sub
why
p,
you
that's S. It's it's S or T equivales T or S. But that's just symmetry of or. And what about this next one? Associativity of a union. That's the same as what? Associativity of or. Idempotency of union. Idempotency of or. Zero of union. As, are you with me? Identity of union. S union, right? Oh, weakening. What about the weakening?
S implies.
Yeah, you know, a subset, right. Okay. S implies S or T, right? Okay. And what about excluded middle? Well, why is this even called excluded middle for sets? Because it's the what? Yeah. So I mean, you know, I'm not asking you to prove very many of these because these are all just, you know, very straightforward. How about basic properties of intersection? Here's basic properties of intersection. Let's take a look at 11.33. Okay, so what do we have? What is that? Come on, what's the predicate calculus for? Yes, symmetry of and, associativity of and, idempotency of and, zero of and, identity of and, strengthening, contradiction. Yeah, that's the one we just did. Yeah? Okay, so aren't those all just very easy? We get all of these for free, right? Almost no work at all. And here's some basic properties of and or, of union and intersection. So distributivity of union over intersection, distributivity of intersection over union. And look, there's a De Morgan's law for sets. Check it out, sports fans.
Sick.
Not, okay, the complement of S union T equals the complement of S intersection the complement of T.
Oh.
But that's just De Morgan's law, not S or, parentheses, S or T, right? Equivales, not S and not T.
So we're going to skip like this whole stuff.
Well, I mean, we just did. I mean, we are seeing that all of these are a natural consequence of the Metatherm. Now, the Metatherm is, I'm not going to prove the Metatherm. It's very tedious to show why, you know, you have to go and,
But you can't prove it.
yeah, oh, absolutely. It can be proved, but it would be very tedious to have to do it. But you can kind of see why, right? I mean, you can. I hope you have a feeling for why it's true. Because the union, because union is based on what? What's the definition of the union? You know, for example, here, what's the definition of union? Let's go back and look at the definition of union. Do you remember what the definition of union is? Axiom union. Here's axiom union 20. It says V is an element of S union T equivales what? You know, S or V is an element of T. So you see the union is very closely related to or. And that's why, and you notice that in the Metatherm, what you do is you replace union with or. Okay? And then similarly, the intersection with and. Similarly, the complement with negation, okay? So anyway, that's where the Metatherm comes from, all right? Okay, but now we reach a section of theorems where, and I need to give you a note here, because am I asking you to prove one of these? 43, 44, 45, and 46? Okay, now look, my question is this. What about 1143 all the way through 1148? So theorems 1143 through 1148. And I don't know why, but no matter how much I emphasize this, people try to use the Metatherm to prove this group of theorems. Now, do you understand why you can't use the Metatherm to prove any of these? Well, because what, you know, yeah, exactly. Well, and the implies, right? See, what this is this is an implies. These expressions are all what kind of expressions? They're Booleans. Are you with me? So the point, they're not set expressions. Do you see what I mean? So look, these theorems, these are Boolean expressions. These are Boolean expressions. These are Boolean expressions, not set expressions. So, you cannot use the Metatherm. To prove them. And for some reason, people always, you know, when I assign one of these or something, people always, oh, they've used the Metatherm, they go try to use the Metatherm, but it doesn't work because these are not set expressions. Okay? No, and you obviously, and the old rule still applies. You can't use case analysis. Well, case analysis would be really hard to do here because what's your case? I mean, your P, where's your P and your Q to be true and false? You know.
How do you? What do you do? Can you use the Metatherm like if you manipulate it in some way?
If
How do you prove those? Because I'm trying to do the first homework assignment.
Well, I mean, these are Boolean expressions. So how would you prove any Boolean expression, right? I mean, you know, for implies, you've got, I don't know, your old friend. I mean, you've got all the things that you did before. You've got your old friend 3.59, or.
What about that V as an arbitrary element? Can you use that kind of stuff?
Well, no. Yeah, but no, hold on. The way you, when you say if the time to use let V be an arbitrary element is when you're trying to prove that two sets are equal. Now, but there's no two sets are equal. You know, are you with me? Well, except for one thing. Hold on. Except for one thing. Check this out. I'll give you some hints here. On the other hand, here, let's take a look at 1147 and 1148. 1147, 1148, what we have on the left-hand side is a two sets are equal. Right?
Yeah, but you can prove that.
Well,
How can S or T be equal to the universe?
No. It's not saying, the theorem is not just that. The theorem is that equals this. Are you you said how could S union T? Well, you were thinking of this is the theorem. No, that's not the theorem. It's that this equals this.
Element to get to equal this.
Well, actually, in this case, I think you're better to go back to for 11.47. I think you'd be well advised to go back to what it means for two sets to be equal, which is extensionality. S equals T, and look at this. Two sets equals for all x blah blah blah, and doesn't that look very similar to?
Yeah, sure.
Are you and that doesn't that look very similar to for all x blah blah blah? Okay, and the same thing here. This set equals this. I think, yeah, extensionality would be where to start there. Okay. But the main point I want to emphasize is that 11.43 through 11.48, these are Boolean expressions, not set expressions, so you cannot use the Metatherm to prove them. Now, I want to give you an example of a proof format using the Metatherm. And what we're going to do is we're going to prove 11.51. Okay? So here we have some theorems. 11.49 is, these are set difference theorems. So S minus T equals S intersection the complement of T. 11.50 is S minus T is a subset of S, and so on. And 11.51 is S minus the empty set equals S. Which seems obvious, but we need to prove it. So let me show you. Here's the proof format for using the Metatherm. Proof format for using the Metatherm. All right? And what we'll do is let's prove 11.51, which is S minus the empty set equals S. So now here's what we do. Now first of all, look, there's a set difference here, right? There's an S minus the empty set. But does this Metatherm, oops, let's go back to this where's the Metatherm? But now, does this Metatherm let S, does this Metatherm have set difference here?
No.
It doesn't. Oh, shoot, so maybe we can't use the Metatherm. Did I make a mistake here?
No.
Well, here, let's start off with the whole thing. Let's start off with S minus the empty set equals S. Now this equals by,
11.9.
yeah, 11.49? Is that what you said?
Yeah.
Equals by 11.49
S and complement of
S intersection
intersection complement.
complement of
No. Empty set.
Empty set.
of the empty set, what? Equals what? Equals S. Are you with me? Does everybody see how that followed? Right? But now what do we have? Now we have,
Metatherm.
now we can have it in a form where we can use the Metatherm. Are you with me? So here's how you should write, here's the format. At this point, you need to write down how to use the Metatherm. At this point, you have to make this statement, I insist. By Metatherm 11.25 what? You have to say, by Metatherm. And you have to quote it. 11.25, and which part of the Metatherm are we going to use?
A.
11.25, two sets are equal, right? So you have to say, by Metatherm 11.25a, and now you have to state what the Metatherm says. By this Metatherm, and so what are we saying? What is the statement of the Metatherm? By Metatherm 11.25a, what is valid?
S and not empty set.
Yeah. S, this is an and, this is, no, it's intersection.
Oh, I thought you wanted to know what it was going to be.
Oh, sorry, yeah. Good point. S, intersection, complement, the empty set, equals S, and you have to say is valid, and then if,
That's a lot of writing.
I should have known. A lot of writing. Yeah, you know what this is? It's the world's smallest violin. By Metatherm 11.25. S. No. You have to say. I'm telling you, this is the format that I insist. By Metatherm 11.25a, S intersection the complement of the empty set equals is valid if and only if what? S and not false equivalents S. All right? And you have to write this out. I insist that you quote the Metatherm, which part of the Metatherm, and write this out.
And then you're gonna rewrite.
And now now you see now we can just prove this.
Yeah, but you rewrite that again.
No. We'll start with the left-hand side, get it to the right-hand side. Okay? So, and then we just continue the proof, but now we have this proof. Okay? So S and not false.
Let's take the whole thing.
No, I want to do it like this. No.
You take the whole
S and not false is by what? Not false is what?
True.
What is that theorem?
definition of false.
Definition of false is
3 point what?
true.
Definition of false is quite sufficient.
Somebody have a number for us?
Why do you need a number? We're so insistent on a number.
Is that right?
I think it is. So this is what? S and true equals by what?
Identity of n.
Zero of n.
A 0 or identity?
Identity.
Said,
Well, someone said 0. Identity of and S. Boom. Because, are you with me?
so
Now, does everybody understand how to use this Metatherm, all right? To make it clear, you have to say, you know, you can manipulate it, get it to a form where you can use a Metatherm. You say by Metatherm, you say which one. You say this is valid if and only if this is valid, and then you proceed to prove this. Okay? So no shortcuts, please. All right? Okay, now, this next one, let's do some, what I want to do now is, let's do some proofs. Who went last? Whose turn is it? Yeah, you did. Okay, Kyle?
I went once.
Did you?
I said the empty set was false.
Okay. All right, Ben. Do you have your equation sheets out? Get out your equation sheets. We'll go around the room. Okay? We're going to prove 11.56, which is, all right, and now here, actually, Josh, you're asking for an example of how to prove these ones without the Metatherm. Here's going to be one, okay? Now, here's what we're going to try to prove. We're going to try to prove that for all x range true, P implies Q that equivalents the set over X body P, range P, the set over X range P is a subset of the set over X range Q. All right? Now, and I've given you the hints here. And by the way, we're going to do a couple of steps in our head. You'll like this.
I will.
Yeah, because we're going to do a couple of steps at once, you know. Instead of, we're going to combine some steps here. Okay, so now, what is the subset? You have your 11,
True.
you have your thing, 11.13? So subset 11.13, where V does not occur in P and Q. So what is that?
True.
So for all these that you want me to do is change the letter,
Well, no,
or just do for all x?
for all, well, it'd be for all V. Well, yeah.
That's what I'm saying.
Oh, sorry, right, yeah, for all V. So for all V,
all V
what?
Range V is an element of P.
No, not an element of P. P is an element of, okay, you were right until then. It's for all
V is
V.
an element of
V is an element,
set over x body range P.
yes, set over X range P, yes.
Body
Body.
over x range Q.
Body V
Is an
is an
element.
element,
Yes.
okay,
Sorry.
okay,
V is an element of
okay, good. Okay, so Kyle, check out 11.7. 11.7,
7-1, isn't it?
twice. No, 11.7. You got your equation sheet?
Are you talking to me?
Yeah. Oh, Kale, sorry. Kyle, that was Kyle. Yeah, sorry, Kale.
Isn't that 11-7-1? Because you have different variables.
It really is.
Is it 11.7.1?
Yeah, it is.
Well, 7.1 is the one you kind of
We
made up.
should, you should have done the quantification with x instead.
Well, hold on. What's?
You use x and would
Yeah. Hold on. Yeah. Hold on. Where's my equation
so
sheet?
if you want, you could do change it down, make it x.
Where's my equation sheet? I tell you guys you should have your equation sheet.
I'm looking at it right now. It says,
I don't believe it. I don't have my equation sheet. Thank you.
Prove why I'm right, everybody.
Yes, you're right. 11.7.1. So what's that going to be?
So for all of V range
range P with what?
X replaced by, no, V replaced by X.
Is it X replaced by V or V replaced by X?
X replaced by V. And then body Q with X replaced by V.
Good. Okay. All right, now you get to do 2 steps in 1 because you don't like to write down stuff, right? Okay, so now trading 9.2 and dummy renaming 8.21. So now how are you going to do do you remember how to do trading with for all? It's the original, you remember the original trading?
You get the implies that,
Yes. The
and then you dummy renaming.
so
You could have done. You didn't even need to do dummy renaming if you originally used X instead of V. Just so
no, you have to. Okay. Anyway, so the trading will be what?
would be
P-
implies Q. Well,
Yeah, P with X replaced
Text substitution implies Q.
Q with textual substitution. But then do dummy renaming and change that
And-
for all V to for all X?
Yeah, which you could have done originally. And then-
No, it has to be done this way.
Like, okay, you could have. Okay, you understand? Like back in the.
I know, but look,
Well,
look.
Couldn't you use X when you first introduced the quantification? Because you decided.
No. This gets back, no, the answer is no. Because this gets back to the thing of if this were X, then this X would be different from this X. The X in here would not be the same as that X there. That's
Yeah.
the whole point.
But you just know that. You just know that. It doesn't.
No, you,
That's why 11.7 is there, and then you decided.
That's why
11.7.
11.7.
no. Notice,
11.7 has the X's, the two different X's in there.
I know, and that's why I give you 11.7.1 because
You
you,
said to use 11.7.
well, he's using 11.7, but with, notice that he doesn't have an 11.7.1, but he's using our 11.7.1. That's how you have to use it. Are you with me? That's why I gave you 11.7.1, so to make this step clear.
I still don't get why you can't use X as the.
You could. It'd just be more confusing.
No,
You can.
because because then this X would be different from, this X would be different. Are you saying and make this for all X?
Yeah,
No, because then this X would be different from that
but
X.
it is an 11. It is an 11.7.
It's different.
You said that these two X's are different.
I know. That's why it's confusing.
So that's why.
So yes,
You
you could,
can
but
do
it'd be confusing.
Okay, anyway. Do you, okay. No. No,
I would like this one.
no, it has to be, no, it has to be done, it has to be done this way. Because look, this says where not, the only time you can do this is if not occurs V and P and Q. That's why.
Say what?
That,
This is perfect.
I'm glad you like
You
it.
don't need that though.
No. This subset, look at the proviso on subset 11.13, where not
There
occurs.
is no proviso on subset.
So we did,
11.13.
this is like the same proviso we
There's
had.
no
It's the same,
Homework yesterday.
exactly. It's the same proviso that we did with the homework the
But look,
other
there's
day.
no proviso on the axiom. Subset 11.13. No proviso. There's no proviso. And if you look up at 11.7, the X's are different. So it would be totally fine to use.
Well, I disagree.
Alright.
Anyway,
We just agree to disagree.
Okay.
It's necessary for the property
You
of
can
technical
cut all of
substitution.
that. Okay, I'll watch.
Okay. And then a property of, okay, so, Rochelle, property of textual, so if in P, everywhere there's an X, replace it with V, and then after that, everywhere there's a V, replace it with X, what do you have? Right. Okay? I still maintain that you have to do, that you have to do it that
It
way.
could be for all X. You could, and you would just have two different X's in the quantification.
It would just be confusing.
It might look confusing to the uneducated eye.
So what you're saying is that you would be doing this in your
But
head.
then you wouldn't have to do dummy renaming, and you wouldn't have to do textual substitution.
Yeah.
Because you
It'd be
wouldn't
a
have
shorter
a textual substitution in there. It would be body P with no textual substitution. It would be range P, body Q with for all X. And then
Because after 11.7, you just have for all x, range p, body q. And then
Yeah, I understand what you're saying. You're saying 11.7. You're saying 11.7, and then you'd be saying for all x, p range p body q, right?
Yeah, then
And
you just
without
plug
that,
in, and you don't need dummy, redaiming. You don't need
No.
substitution. You'd be done.
no, because
You just need to realize that when you start off. With
No, no,
one
no.
X, that
No, no,
one
no.
X is bound and the other isn't. This definitely works. Because there's two different x's on 11.7. Those two x's are already different anyway. So you're just introducing a different x.
yeah, the x's are different. So
Yeah,
you have to label them.
because
So you have to label them to be different.
It's not fine to make them the same.
Yeah, he's right. It's not fine to make them the same. They are different. So you need to name them differently. If they are different, then they have to have different names.
But you have two
That's
different
why.
x's in the 11.7 theorem, and those aren't named differently.
I know. That's why I give you 11.7.1.
So makes it more defined that they're different.
I'm saying, like, how could you prove 11.7 if the x's aren't labeled to be different in the first place? Do you get where I'm coming from? 'Cause
Yeah.
they're inherently different.
I understand.
They have to be different. I mean, they are inherently different because when we identify the one x outside the set, that is free, and when we identify the x that's in P inside the set, that is bound. So they have to be different. So you need to name them differently. So they have to be named differently.
You can call the same variable, but it just gets confusing.
But confusing.
Yeah, but but
I'm reducing two steps.
his point is that this is confusing, and you want to.
There's too many textual substitution of variables. Whereas if you just use x, it might be a little confusing for like one step, but it's like you have two less steps.
But the argument that the proof is shorter is not the point. I mean, that's not a valid logical argument. I mean,
Right.
so you see what I'm saying? I think anyway. Okay, so, well, we beat that one to death, didn't we?
Yeah.
All right, okay, so okay, so shall we argue? I know, let's, why don't you just step outside and we'll settle this like men. We'll have some fisticuffs. No. Okay, so here's another one. Let's do another one.
Just agree,
Yeah.
He grades your homework.
11:57. Let me see. Let's take a look. So which one did we just do? 50. Yeah, so we're looking at these. Here's, which one did we just do?
56.
Oh, previous slide. Oh, right, we just did this 56. Okay, so here's some more. 57 is anti-symmetry. This makes sense, doesn't it? S is a subset of T and T is a subset of S. How can that be? The only way that can be is if they're what? Is if they're equal. Well, no. Can you use the Metatherm with this? Yes or no?
No, but it's the same thing.
Right, and then reflexivity, S is a subset of S. Transitivity, S is a subset of T, and T is a subset of U, implies S is a subset of U. Ooh, that's an interesting one. Okay. And there's a bunch of other ones. The empty set is the subset of any set. Okay, and S is a proper subset of T if and only if what? S is a subset of T, and it's not the case that T is a subset of S.
What's a proper subset?
A proper, yeah, you remember, it's that it is a subset but not equal to.
Oh, okay.
Remember that? Okay. And yeah, that's like strictly less than as opposed to less than or equal to. That's sort of like the analogy. And then S is a subset of T, Oh, here, how about this? 11.64, that's interesting. S is not a proper subset of itself. Makes sense, right? In other words, it's not the case that 3 is less than 3, okay, by analogy. That's not a proof, by the way. You can't say, oh, because proof by analogy. Okay, 11.65, 65, S is a proper subset of T implies S is a subset of T. Make sense?
Yeah.
And then S is a
So
proper
does that
subset.
mean that S is smaller than T?
The number of elements. The pound S.
Yeah.
Oh, that should be a theorem. That would be a nice thing to prove.
Pound S is less.
Pound, yeah, that S is a proper subset of T implies pound S is less than pound T. But that's not I don't think we have that theorem. You might want to try to prove that. That might be kind of hard to prove, actually.
Do we have any theorems about pound?
Pound, oh yeah, we have remember we have the definition of pound. It's it's sigma over I of 1, remember? Range R, body
Use
1.
induction for that?
I'm not sure how you would prove that, actually. I've never thought about that
Do
one
it.
before. Okay, and then we have some transitivity ones. S is a subset of T, and T is a proper subset of U implies S is a proper subset of U, and so on. Okay, so now here's another one that we can prove. Let's do 11.70. Let's prove 11.68. What is 11.68? S is a subset of T implies T is not a proper subset of S.
Which one is that?
1168. Oh, sorry. I wasn't quoting 1168. 1168 is S is a subset of T, and now this U, that's another set. That's not the universe. Can you tell the difference?
Yeah.
By the font there. And U is and it's not the case that U is a subset of T. That implies that it's not the case that U is a subset of S.
S is a subset of T, and U is not.
What is that saying anyway? Here.
Oh, okay. Yeah, that makes sense.
Does it make sense? So what? Here what we have, S is a subset of T. So if this is the universe, okay, and if we have S here, and what are we saying? S is a subset of T. So let's say that S, so if this is, no,
That's T.
yeah, this, so if this is T,
Here's S,
and this is S,
and U is not a subset.
and U is not a subset of T, so U is somewhere else. So U is something like this, right?
And U is not a subset of S.
Then it's saying that U can't be a subset of S,
Because then it would have to be completely confined within S, which would make it.
which would make it not, yeah. Okay, so that's what it's saying. All right? I hesitate
Contradiction.
to start this because I think maybe we can do it.
You got 4 minutes.
Okay.
Pound S.
All right, so here it is. S is a subset of T, and it's not the case that U is a subset of T, implies it's not the case that U is a subset. We're going to start with the left, and we're going to get it to do what? Imply the right. Okay, so Rochelle, are you ready? You're up. Oh, you did? Oh, that's right, you did. Mason, you're up. Okay, S is a subset of T, and it's not the case that U is a subset of T, equals, now, by subset 1113. And what we're going to do is we're going to do the subset on the U. We're going to do it on the right one, not the left one. We're going to use the subset 11.13 on that U as not U as a subset of T. Are you with me?
Okay. That makes for all.
So we'll bring down the S as a subset of T, and so what is it? A for all?
And so is it not for all?
It's not for all.
X.
U.
Range what?
Range X is element
Of U.
of U.
Body
Body X is an element of
T. Yes. And now, Kyle, can you do generalized De Morgan on what he just said? Because we're going to do 2 steps in 1. You like this?
We're using 1115 and De Morgan on just the.
And generalized De Morgan on the right side. So do you remember what he said?
Why don't you do it on the
I
left
remember
side
what
as
he
well?
said.
None.
Why don't you do it on the left side as well?
Just hold your horses.
Alright, hold on.
Okay, so that means that
So not for all turns into a what?
existential.
Yes, so that turns into an exist, and then what do you do to the body?
Not it.
Not it.
You knot it, okay?
Not it.
Not it.
Not it.
Is that right?
Go for your head.
Not? Is that right?
Yeah.
Well,
Yeah.
Not, because,
took a shortcut.
well, the not in front is the same as not an element of. Are you with me?
Yeah.
Okay.
Ah.
Ben? Distributivity of and over there exists. So now we're going to pull it in. Watch this.
That's why you didn't do
Pull it in.
So can you pull it in?
Good.
That is.
Are we only working? Okay. It'll be. There exists an
X.
range. X is an element of U.
Yes. Body.
S is a subset of T,
Yes.
and X is not an element of T.
Yes. Are you with me? Okay, Kale. Subset 11.13 and trading 9.2. Can you do those two at once?
So then for the subset, it'd be for all of x, x is an element of s, and x is an element of t. And then,
Let's make it for all y. Oh, sorry. For all x, x is u, right.
and then the trading would be,
You want to use trading 9.2?
You want to use trading in the for all with the subset.
so it'd be for all of x,
Only you have to make a different variable, y.
y. Range body.
Range true body,
X is an element of s.
y is an element of s.
Y is an element of s implied.
Yes, very good. Okay, you want to do this one? Josh, monotonicity, has everybody got this? Okay. Josh, what do you think? Monotonicity of there exists, 9.27, using instantiation 9.13. Oh my goodness.
Well, that means it's true for one of them.
And notice what we have here. Notice what we have here. Implies. Are you with me?
Oh.
Um,
And I end up with the right side of monotonicity.
gotcha.
Because don't we have something that if this one implies something,
Are we
then
using
by
T
mon.
implies?
Well, you know, well, okay,
Instantiation is an implication, and so is monotonicity.
Right. right.
I was using like the strength of it.
So it's this.
Where did the instantiation come from?
Well, for all y, if it's true for all, that implies it's true for one.
Right.
Are you with me?
Well, where did that?
And then if the body, and then we use monotonicity of over and there's a monotonicity of the, you know, didn't we have like if P, well,
Q implies P.
yeah.
That there exists,
I-
blah, blah, blah.
yeah, I see now we should not have started this because it's time to go. So anyway, let's just look at it. So, but now what about contrapositive? Oh, this one's easy. Contrapositive,
Flip them and make them negative.
flip them and make them negative, okay?
Make them negative.
And now, 3.66, P and P implies Q equals what?
P and P implies Q.
So that'll be what? There exists an X,
P and Q.
range X is an element of U, what?
X. Body.
Quick.
X is not of T.
In,
X is not of X.
yes. And then monotonicity, blah, 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 and then generalize the Morgan, and boom, and we're done. Well, that was a pretty involved one.
Is that the simplest way to do it?
I think there's.
I think there is. I don't think
Please don't
so.
put down the test.
I don't think so.
I think there's an easier way to do it.
I think what's going to happen is probably, if, we'll probably spend a lot of time next week answering questions about the homework.
Reviewing and all that. Do we have like a bunch of review time left?
See you next time.
Do we have review